Okay, so what we can do is we first want to measure the spectrum of a solution to find out what wavelength to use. And so first thing we're going to do is we're going to zero the spectrometer by putting in the blank. Okay, and now what we're going to do is we're going to look at our most concentrated solution of our standards. And what we see is that the maximum of the wavelength, you generally want to take the maximum of the absorption spectrum, so that if the wavelength ranges a little bit left or right, it doesn't change the absorbance very much. So we're going to move over to there and choose a wavelength somewhere near the top here. So let's say that's 807 nanometers, looks pretty good. Let's go to 800 and let's go to 810, make it for that. It's 810, and we have that reading, our first reading, and that is for sample A, it's 0.69 absorbance units. Okay. All right, then we'll look at the our other ones at that same wavelength. Sample B, that is 0.555 absorbance units. Sample C, 0.382. Sample D, 0.266. And sample E, 0.137. And finally, we want to do our unknown solution, the solution of our unknown compound. And the absorbance for that solution at that same wavelength is 0.544 absorbance units. All right, so that's all the measurements we're making. Class, the visible portion of the electromagnetic spectrum goes from 400 nanometers to 700 nanometers. And we just made our final measurements at 810 nanometers. And the title of this experiment is UV visible absorption spectroscopy. And it is not lost upon me that your final measurements are made outside of those regions of the electromagnetic spectrum. But so be it. So your final task is to take the data that we just came up with and that we just measured, and to use that to figure out the identity of the copper compound that we were measuring, and that will be explained next. All the experiments have been done and all the data has been collected, and finally we need to do the calculations required to answer our question as to whether or not the waters of hydration have been lost. So the first thing we're going to do is calculate the concentration of the standard samples. Those were made using copper sulfate, and we know the masses for those. Then we're going to create a standard curve, just like you did for nickel, between the concentration of the standards and the absorbance of the standards. And from that, we'll get the equation of the line that relates the concentration and the absorbance for copper. Because we know the absorbance of the copper hydrate sample, we can now determine the concentration of the copper. This is similar to what we did for the nickel case, where what we've done is we've used known solutions and Beer's law to measure absorbance, measure the concentrations. We know B, and therefore we determine the absorptivity coefficient for the copper. That absorptivity coefficient can be used then when we have a solution for which we don't know the concentration. And so for our hydrate solution, we're going to know the absorptivity coefficient, we're going to measure the absorbance, and from that we'll calculate the concentration of the copper. Once we know the concentration of the copper, we can determine the number of moles of that because we know the volume of the solution. Once we know the number of moles of the copper in the solution, we can determine its molar mass. The data we'll be using is the data we used in the experiment, plus a couple of things that weren't mentioned yet. First of all, the standards were made up using copper sulfate pentahydrate, which has a molar mass of 249.67 grams per mole. This table gives the masses that were used and the absorbances that we measured a minute ago, and the volume of those solutions was 250 milliliters, or of course 0.250 liters. So from that you can determine the concentrations of the standard solutions and then make your standard plot. For the hydrate, The hydrate solution was also made up in 250 milliliter volumetric flask, so it's 0.25 liters, and the mass of the hydrate compound used was 1.865 grams. So once you determine the number of moles of the copper, which you do by multiplying the volume of the copper solution made, 0.25 liters, times the concentration of the copper you get after using the standard plot, you multiply those together, you get the moles of copper. You'll take the mass of the copper compound, divide by the moles of copper that we measured, and that will give you the molar mass. Once you have the molar mass, you can answer the final question, which is, has it dropped very significantly from the copper dihydrate molar mass of 170.48 grams per mole?